Let us discuss the concept of even and odd extensions of a function in order to find its Fourier series. Consider the bump function shown, where I only defined it between 0 and 2 as follows. F of x is equal to 1 between 0 and 1, with the endpoints left out, and f of x equals 0 between 1 and 2. This function, as written, cannot be expanded in a Fourier series because it does not have any periodicity whatsoever. There are two ways in which we can make this function periodic, and they are referred to as the even and odd extensions. The even extension would be the reflection of this function about the y-axis. If I reflected this function about the y-axis, then the graph I would get would be this one, where the function would be 1 between 0 and -1 and 0 between -1 and -2. And then I periodically extend this with a period of 2 on this side and -2 on that side. In other words, my value for L minus L comma L would correspond to -2 comma 2, with this function being periodically repeated. Now this even extension is the very bump function that I had in an example from one of the videos last week, and I will not do that. The other extension is the one that concerns me, and that's called the odd extension. The odd extension of this function is the one where you reflect it about the origin. If you did that, you'll find that you get this. Between 0 and -1, this function takes a value -1, and from -1 to -2, it takes a value 0 again. So that's called the even extension of this, and this is called the odd extension of this function. The odd extensions also have a periodicity, so I can think of this as being defined from -2 up to -1, and then from -2 to 0, and from 0 to 2. So that also has got the same periodicity that we have earlier. The even function, the even extension of a function, is defined as 1/2 f of x plus f of minus x. That's a formal definition, and this is how we are able to obtain the even extension. The 1/2 is there so that you don't double the values. So if you notice, for the even extension, all I would have to do is f of minus x, which is not even defined at this point, but can be extended like this. Then f of x would just be 1/2 the average of f of x and f of minus x. So it's 1 minus 1, and then if you define the value at 1 and you find the value at -1, it's both equal to 1, so that'll be 2, and 2 divided by 2 is 1. So it makes sense. And the reason this is an even extension is, if we try to put x equal to minus x, we're going to get 1/2 f of minus x plus f of minus x, which is just f of x, and it's the same function. Well, that is the mathematical definition of an even function. If we tried the odd extension, that's going to be 1/2 f of x minus f of minus x. So this is guaranteed to produce an odd function, because if we tried sticking the argument -x in, I'm going to get 1/2 f of -x minus f of positive x, and that's negative f odd x, which is the mathematical definition of an odd function. Now when you have an even function, the series that you get is called the Fourier cosine series, and if you have the odd function, the series that you get is called the Fourier sine series. So in this particular example, if I do the odd example now, I can expect to see a Fourier sine series. The reason for this is quite simple. The Fourier cosine series has terms like an, including a naught, by the way. So that's going to be 1 over 2l actually it's 1 over L. The integral from minus L to L, f even times cosine n pi x over L dx. Well, that is the definition of the coefficients a sub n. Now the reason this is the only coefficients that you get for an even function is an even function times cosine, which is another even function. The whole thing is another even function. The product of two even functions is an even function. And an even function integrated between symmetric limits gives you a non-zero answer. Similarly, here I get Bn equals 1 over L integral minus L to L f odd sine n pi x over L dx, and that is also not equal to 0, because an odd function times sine n pi x over L, which is another odd function, gives you an even function. The product of two odd functions is an even function. Anything else, if I tried putting cosine here with odd, I'll get an odd function, and that'll be 0 between even limits. For example, here if I put sine of n pi x over L, that is an odd function. Odd times even is again an odd function, and that'll give me a 0 answer between symmetric limits. So these are the only things that survive for an even extension, and for the odd extension, the sine terms are the only ones that survive. All right, now let us go ahead and try to execute our plan. I'm going to find now the odd extension of this function as defined above in the figure. So I know that f odd x has to be sum from n equals 1 to infinity Bn sine n pi x over L. In other words, it's just a Fourier sine series, with Bn itself defined by 2 over L. Observe this. I'm writing 1 over L, negative L to L, as 2 over L, 0 to L. That can be done because of symmetry. All I would now have to do is evaluate this integral, which is not that difficult. L is equal to 2 in this case, so I'll put that, give me 2 over 2, which is 1, integral 0 to 2. But from 0 to 1, the value is 1. From 1 to 2, the value is 0. So I only write from 0 to 1, sine of n pi x over L, which in this case is 2. The integral of sine is this negative cosine, so that's negative 2 over n pi cosine n pi x over 2 between 0 and 1. So that's going to give me negative 2 over n pi cosine n pi over 2 minus cosine 0, which is 1. It might be a good idea to split this up into even and odd, just to see what happens for each case. So if n is even, then I'm going to get b2m equals negative 2 over 2m pi cosine of 2m pi over 2, which is just m pi, minus 1, and that's going to give me negative 1 over m pi times negative 1 to the power m minus 1. What I will now do is to take the negative sign inside, so I get 1 over m pi negative 1 to the power m plus 1 plus 1. Let's try the odd case. If n is odd, then b2m plus 1 is going to be negative 2 over 2m plus 1 times pi cosine of 2m plus 1 pi over 2 minus cosine of 0, which is 1. Cosine of an odd number times pi over 2 is always 0, like cosine pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and so on. So that's 0. So that just gives me the negative and the negatives cancel out. So it gives me 2 over 2m plus 1 times pi. So we have a formula for both even and odds, and now it's just a question of gathering everything together and writing the answer. Let's write the answer. F odd of x is the sum m even equals 0 to infinity of 1 over m pi minus 1 to the m plus 1 sine of, if n is equal to 2m, I'm going to get 2m pi x over 2. So that's going to be m pi x. Plus the sum from m odd numbers start with, also I think with 0, because m equals 0 gives you the first odd number, to infinity. 1, actually it's 2 over 2m plus 1 pi sine of 2m plus 1 pi x over 2. That is the answer. Let's try to see what this answer looks like for some values. If m equals 0, then regardless of what that is, sine of 0 is 0, so that goes away. The next even number is m equals 2. If m equals 2, I'm going to get 2 pi here, and that, but that's going to be 2 plus 1 or 3. 3, hang on, m equals 1. I'll get 1 plus 1, which is 2, so that works. I get 1 over pi 2 sine of pi x. For m equals 2, I'll get 2 plus 1, 3, and that's minus 1 to the power 3, which is minus 1, plus 1, which is 0. Then I have to go to m equals 3. 3 plus 1, 4, so that gives me 2 again. Only odd values of m contribute. So I get 3 pi 2 sine 3 pi x plus 1 over 5 pi 2 sine 5 pi x, and so on from this one. What about the odd sum? From the odd sums, I notice that when m equals 0, I'll get sine of pi x over 2, and this gives me again 2 over pi. So 2 over pi sine of pi x over 2 plus, now if m equals 1, I'll get 2 over 3 pi sine of 3 pi x over 2. So here I get everything. 5 pi sine of 5 pi x over 2 plus, and so on. So that's the complicated situation for the odd extension. Let's take an example of some value. How about f odd at value 1? By the Dirichlet theorem, since at x equals 1, you have a jump discontinuity, the value of the function is going to be exactly half. So that gives me 1/2. Let's see what the right hand side predicts for us. If x equals 1, sine of pi, sine of 3 pi, sine of 5 pi, all those things vanish. So the entire top thing vanishes. All I have left is 2 over pi sine of pi by 2 plus 2 over 3 pi sine of 3 pi over 2 plus 2 over 5 pi sine of 5 pi over 2, and so forth. Sine of pi over 2 is 1, sine of 3 pi over 2 is minus 1, sine of 5 pi over 2 is again 1. So this keeps alternating. So this tells me that 1/2 equals 2 over pi times a very familiar series, which is 1 minus 1/3 plus 1/5 minus 1/7. So this is exactly the series for pi over 4. So the old series for pi over 4 is recovered, which we saw in the earlier videos. And so we have confidence that this value, this whole procedure makes sense.